So today's topic of discussion is of advanced communication system, and we are going to discuss free space radio wave propagation and path loss in this first lecture. And in this, we are going to have already covered multipath. We have already covered fading and shadowing as part of the theory part. And today's lab part, we are going to discuss upon how to calculate the path loss for free space radio wave propagation, and we are going to use Python for doing our evaluation today. So I'll briefly define what is the objective of today's lab session, how we are going to do this, and then we'll go to the theory and the concept of today's lab session, like basic formulas guiding the calculation of path loss and the free space path loss for the radio wave propagation, and how we will going to implement using Python, some implementation step. One basic example will be discussed in today's session. And based on this session, we will be analyzing what is the observation of the problem statement that we are going to solve today and what is the learning from that. So for your lab session, we are going to follow this format, and I would suggest for this evaluation of lab sessions, we'll follow this 4 major points, and for any assignments that I'm going to assign you, you have to follow these 4 points only for preparing the assignments. Okay. So today's objective is to understand how receive power, when we are having the radio wave propagation, I've discussed this in our first lecture, how multipath effect is causing the receive power to fluctuate as the distance between the transmitter and receiver is increasing. So we have already discussed what are the different factors affecting the free space radio wave propagation. I'll just simply summarize in few points. The first point was reflection from any large object. Large object means the size of the object is greater than the wavelength of the signal being transmitted by the transmitter. So that was first criteria, that was called reflection. Second criteria was diffraction. Diffraction means when the signal transmitted from the transmitter is hitting any sharp edges. It can be sharp edge of a building, it can be sharp any object that is there. So any sharp edge, when it is hitting, there is bending of the signal. Now this bending of the signal is called diffraction. And third criteria was scattering, which is when the obstacle that is in place of your transmitted signal is the size of that obstacle is less than the wavelength of the transmitted signal. So first criteria was when we are having reflection, that means the size of the object is greater than the wavelength of the transmitted signal, that is reflection. Second criteria was diffraction. Diffraction does not depend upon the wavelength, it is only because of the sharp edge there is some bending. And third criteria was if the size of the object is less than the wavelength of the transmitted signal. So we had reflection, we had diffraction, and we have scattering. So these 3 are the main parameters based on which we would have variation in the signal propagation from the transmitter to the receiver. Now, based on these parameters, again, after this also, you will have one more parameter, which is called refraction. So refraction means when there is bending of a signal, when it is transmitting from one density medium to another density medium. That means when there is variation in the density of the medium. So it can be between the atmospheric layers, it can be between water and other material like oil, it can be air and water. So different kinds of materials will result in different nature of the propagation of the wave when it is passing through various mediums in this from between the transmitter and the receiver. So all these factors are very important for studying what is the effect of all these factors on the radio wave propagation. So in our previous lecture, we have already discussed that all these factors cause something which is called multi-path effect. Now, multi-path effect, I'm just writing MPE here. So what is multi-path effect? So multi-path means a signal, suppose there is one transmitter and there is one receiver here. So when the transmitter and the receiver are both facing each other face to face, that means there is line of sight communication. So when there is face to face or they are like directly pointed to each other, this is called line of sight communication, where the receiver is able to see the transmitter, and the signal from the transmitter can directly go from the transmitter to the receiver. This path between the transmitter and the receiver is the shortest path of communication. Okay. Now, when does this multipath effect comes into play? This multipath effect comes into play when you have different obstacles in between this channel, communication channel. Obstacles means there are some buildings, high-rise buildings, there are some vehicles, there are some, you can say mobile towers, you can have different kinds like forest, cover, hills or mountains. So when there are different size of obstacles in this communication channel through which the signal is being transmitted from the transmitter to the receiver, then what happens is these factors come into play. Now, these factors means there would be some amount of reflection, there would be some amount of diffraction, there would be some amount of scattering, there would be some amount of refraction. Now, because of all these factors, what is happening? The signal from the transmitter will have different path from the transmitter to the receiver. They will follow different path. So the first path, let's suppose, is this path, which is traveling a larger distance compared to the direct line of sight transmission. Again, second path is suppose this path, where some amount of reflection, some amount of diffraction, or some amount of scattering can happen. Combined effect of all three can happen. And this signal is coming, again, it is deviated multiple times from the transmitter and it's reaching the receiver. Now, when the receiver is receiving the signal, now same signal is being transmitted from the transmitter. So transmitter is sending same signal in 1, 2, and 3. Let's take this as 3. Okay. So same signal is being transmitted in all these 3 channels. But when these 3 signals are being received at the receiver end, what is happening? We're going to have the combination of 1, the combination with 2 and 3. So when we are having different copies of the same signal being transmitted by the transmitter, but they are traveling different path lengths. Different path length means as this is traveling larger distance, that means time taken by this signal to receive receiver will be more compared to the signal which is coming by direct path. Okay. Similarly, the second signal that is coming by multiple reflection, scattering and diffraction, the distance traveled by this signal is more compared to the direct path. So the time taken by this signal would be more compared to this direct path also. Now, why this difference in time taken by all the signals to reach the receiver? This is because of these factors that I've already mentioned in my previous lecture. Now, when these signals arrive at the receiver side, all these signals 1, 2 and 3 are same signal generated by the transmitter having same amplitude, that means same power levels and same phase at the transmitter side. But when they are received at the receiver side, we find that the signals will have different amplitude, they will have different phase. So combined effect of all these 3 at the receiver side would be different compared to the signal which is generated at the transmitter end. Okay. So this is called multipath effect. So multipath means the signal which is generated from the transmitter is following different path because of different obstacles present in the path or the channel, and they will suffer different kinds of phenomena due to these obstacles. Now they are traveling different path means the distance traveled by each signal is different. Distance traveled is different means the time taken by each signal to come at the receiver's side is different. Okay. So due to this multipath effect, there is some amount of time delay. Okay. Just let me denote this as tau. So there is delay in the signals which are being received at the receiver side. Why? Because of this multipath effect, they are traveling different distances. Clear? So today we are going to understand how the received signal power. So when I'm receiving the signal, I'm receiving a combination of all the 3 types of signals. One is the direct path, the 2 are reflection, scattering or diffraction, different kinds of signals following different path lengths. So they are received at the receiver side. Now the combined effect of all these signals, how the received power is changing if I change the distance between the two. That means if I change the distance between the transmitter and the receiver. Okay. So if I change the distance between the transmitter and receiver, how this received power is changing. And if I change the carrier frequency, frequency means the frequency of the transmitted signal. So if I change the frequency of the transmitted signal, how the received power will change with respect to frequency, and how this will depend upon the distance between the transmitter and the receiver. So this is our main objective to understand for this lab session. Okay. So in this lab session, we are going to focus mostly on the radio wave propagation through wireless communication channel. In this channel, different types of path loss will be incorporated because of different kind of multipath effect. I've discussed all the different factors which are important for your multipath effect. And we will follow one formula for calculation of received power. We will discuss this now. So basic theory is there is one transmitter and there is one receiver, and the distance between them is denoted by small d. Now, when the signal is being transmitted from the transmitter, it is suppose having a power of PT, the transmitted power. Now, power, if you are seeing here, generally power is given in watts. Okay. So some amount of power is generated here. That signal is being transmitted by the transmitter. It is being released in this channel, wireless communication channel. Now it is being propagated from the transmitter to the receiver. It is going to cover the distance small d, and it is being received at the receiver side. Now when the signal is received at the receiver side, let's say the power received is PR. Okay. Now because of this presence of channel here, this channel can be any medium, it can be any obstacle, it can be any combination of mediums, air and water, or water and oil, or different mediums. It can have different kinds of parameters affecting the signal propagation, like reflection, diffraction, scattering. So different kinds of phenomena. So because of this, we experience, or we come across a term which is called path loss in radio propagation mechanism. What is this path loss? Path loss is nothing but the reduction in the signal power with respect to the distance between the transmitter and the receiver. That means the power of the signal that is being transmitted is different from the power that is being received at the receiver side. Okay. The thumb rule is this power is more compared to the receiver power. So because the received power strength is less, we are denoting this as path loss. Why? Because we are losing some amount of power in this communication path or channel. Okay. So what amount of power I'm losing in the channel is given by this path loss formula. That is nothing but PL is equals to power transmitted. That means signal power that is being transmitted. You can take this in watt directly, and the ratio is with respect to the power that is received at the receiver side, which is always lower than the transmitted power. So if we are denoting this ratio we will take it as normal watts. If the power is given in watts, you will just simply put that ratio and generate the path loss. But generally, we also calculate path loss in dB or decibel scales. So when you are doing in decibel scales, it is nothing but 10 log base 10 of this ratio. Okay. So in this case, your transmitted power and received power, both of them would be in dB scale. So when you are having in dB scale, you will simply do what? When you are doing power, if it is given in dB, you will simply division is replaced by subtraction here. Okay. So if your power is given in dB scale, so if it is in dB scale, you will simply do subtraction of the power levels. So when both of the transmitted and received power is given in dB scale, then your path loss in dB is nothing but transmitted power in dB minus received power in dB. So this ratio becomes subtraction. It is replaced by simple subtraction. So if it is a multiplication in normal equation, in dB scale, it would become addition. If it is division, it becomes subtraction. So very plain, simple equation we have. So first equation is simple ratio if the power is given in watts, and if it is given in dB, you will use this formula. Okay. So next, this is what is called path loss. Now, if we want to calculate the power received at the receiver side, then what are the factors that receive power is dependent upon? This power received, that means the received signal power is dependent upon the power of the transmitted signal, the gain of the transmitting antenna, the gain of the receiving antenna, and it also depends upon the wavelength of the transmitted signal. Now, wavelength, why? Because we have a component which is called frequency. So whenever there is a frequency component in propagation sense, we always calculate this with respect to wavelength. Why? Because wavelength is the length, or the unit is in centimeters, meters, or millimeters. That means it's a path, propagation path unit length. Okay. So every frequency or every frequency component of the transmitted signal will have a corresponding wavelength. So this wavelength is a parameter corresponding to the signal which is generated at the transmitted end. So every frequency will have some wavelength. Now, what is the relationship between wavelength and frequency? Wavelength is nothing but the speed of the light divided by frequency. Okay. So this is very plain simple formula again. Now this divided by 4 pi d. Now what is this d? D is nothing but the distance between the transmitter and the receiver. Okay. Now this reflected signal is dependent upon these three parameters: frequency or the wavelength of the transmitted signal and the distance between the transmitter and the receiver. Okay. And it is also proportional to the square of this parameter. That means receive power is directly proportional to transmitter power, transmitted signal power, transmitter antenna gain, receiver antenna gain, and it is directly proportional to the square of the wavelength of the transmitted signal. But it is inversely proportional to the square of the distance between the transmitter and the receiver. That means more the distance between the transmitter and the receiver, less is the receiver power. Why I'm doing 2 times downwards arrow? Because it is proportional to the square of the distance. So inversely proportional to the square of the distance means even a slight increase in the distance will result in very big variation or reduction in the received signal power. Okay, so this equation is very, very important. Then in dB scale, this equation can be written as this given here. So power received in dB is equals to transmitted power in dB plus the gain of the antenna both at the transmitter and the receiver side, and we have the wavelength component, we have the other, these are all fixed parameters. Wavelength is because of the frequency, this is a fixed parameter, 4 pi will always have a fixed value, and D is another variable parameter here. Why? Because distance of the transmitter and the receiver can change. Why I'm saying it can change? Because in wireless communication, your transmitting antenna can be on a vehicle, your receiving antenna can be also on a vehicle. When both of the vehicles are moving, so the distance between the transmitter and the receiver is always changing. So with change in this transmitter and receiver distance, how the signal that is being received at the receiver side is varying, how the power is varying. That is the objective of our study here. Okay. So in terms of path loss, you will use this formula. I have simply discussed this. This is in dB scale. If you want, you can use this formula directly. If this is given, then you can use this formula. Now, there is one more factor that you need to consider here. In your exam, if you have anything which is called isotropic antennas. Isotropic antenna means this is specific to antenna and propagation here, but we are going to use this term very frequently while solving more numericals. So what is isotropic antennas or isotropic radiators? Isotropic antennas means the antenna which is radiating equally in all directions with same power. So when it is radiating equally with same power in all direction, the gain of such antennas become 1. Why? Because it is radiating uniformly. So if the transmitter and the receiver, both these antennas are isotropic antennas, then you should always take the gain of the transmitter and the receiver antenna as 1. Okay. So everywhere, wherever you are having GT and GR in the equation, you will take this as 1. Clear? Okay. Now the distance here, it can be given in kilometers, it can be given in meters. Accordingly, you will be substituting here. So in this equation, we are taking it in kilometers. So if distance is given in the question as meters, convert this as kilometers and simply calculate this formula. A frequency here is given in megahertz. So if you have frequency given in gigahertz, convert it accordingly. Okay. Now the received power in dBm, in short, we can write this as the final formula where it is dependent upon the transmitted signal power in dB, gain of the antenna in dB, transmitting antenna, gain of the receiving antenna in dB, and the path loss. So we are always doing subtraction of the loss factor here. That means every time the transmitted signal power is more compared to the received signal power. And what is the amount by which it is deteriorating? It is deteriorating by the amount which is indicated as the path loss. This path loss is because of this medium in between. And as the distance is increasing between the transmitter and receiver, this path loss will further increase. Okay. So if I am having isotropic antennas, remember to take the gain value as 1. And this is how the formula for path loss can be calculated in dB. So we'll quickly go to one numerical and then we will quickly go to the lab part of this. So in the numerical here is for one frequency component, that is 2.4 gigahertz. From this frequency components, you have to find out what is the value of the wavelength. So wavelength is nothing but speed of light divided by frequency. You know what is the speed of light? It's a fixed constant parameter and the frequency is already mentioned in this numerical here. Transmitted power is already given in dB. Gain of the antenna, transmitting antenna is already given in dB. Gain of the receiving antenna is already given in dB. And the distance between the transmitter and the receiver is given in meters here. You have to calculate what is the received power in dB for this and what is the free space path loss. So there are two parameters actually. Okay, so these are the formulas that we are going to use. So I've just listed out the formulas and what are the given parameters that are there. So I'm just writing this down as what is given here. So we have the transmitter power, gain of the transmitting antenna, receiving antenna gain, frequency that is there, the distance between them, and what is the speed of light parameter here. Okay, so the first step is always to calculate the wavelength from the given frequency. So from here we will calculate the wavelength in meters. From path loss formula, we will put the value of D here. Now, if you see here, your wavelength is calculated in meters here. That means this is in meters. So your distance should also be in meters here when you're substituting, not in kilometer, not in any other unit. Why? Because this is a fraction. So this meter and this meter should cancel each other. So when you're doing a ratio of length, it should be in the same unit. So if you substitute the value of D in meters, the wavelength should also be in meters here. Okay. Now you just simply substitute the value here. You will get the value of the path loss in dB. Yeah. So this is the second step. Third step is how to calculate the receive power. Now we have already studied receive power in dB is dependent upon the transmitter power. It is dependent upon the gain of the transmitting antenna. It is dependent upon the gain of the receiving antenna minus the path loss. So these are the given parameters. This is the calculated parameters. Simply you will find that the receive power is minus 48 dBm. Now you see here, transmitted power is 30 dBm, but receive power is minus 40 dBm. Now can you tell me how much is the difference between the transmitted and the receive power? So transmitter power is 30, but receive power is minus 48. So what is the difference between the two? The difference is minus of this. So this is nothing but 30 plus 48. So this is 78 dB difference. So this is the amount of power difference between the transmitted and the received signal. That means transmitted signal is 78 dB higher than the received signal. So you can understand that received signal power is very, very, very low compared to the transmitted signal power. Okay. So from this numerical, we can just conclude stating that based on 100-meter distance, the path loss is very high, and based on that, the received signal power is very, very low. So this is my final conclusion from this evaluation of this numerical. Okay. Now, how you're going to do this in Python? We are going to follow very simple Python code here, and you can use Google Colab. You can use any other platform for simulating this Python code. I'm giving you this one as an example for the numerical that I have just discussed. So based on this, this is the program, and I'll give you one assignment which is a little bit harder version of this, but I'm expecting you would be able to do this because it is using the same formula, but the evaluation would be different. Okay. So for doing any kind of mathematical analysis, we will always use the package which is called NumPy. NumPy has been denoted here as NP. So everywhere where we are using any mathematical formula, like we are using log or we are using pi, so these functions, when we are using, we'll use the NumPy package. So here, that is why it is written as np log of 10, and it is written as np.py. Why? Because Python uses this NumPy package for doing mathematical evaluation of functions, for calling those functions. Okay. We are also going to use matplotlib library file, pyplot, to plot different parameters in x-axis and y-axis to see how the path loss is varying with distance, how the receive power is varying with distance. So these are the given parameters that are there. Define it using any variable, and then you do the calculation for wavelength, you do the calculation for path loss, you do the calculation, direct formulas for receive power, and you can do final value printing. So you'll get the final value printed as here, that is the expected output. Simple as possible. Okay. Another way of using plot function. So I've used here plot functions to plot different parameters. What are we plotting here? We are going to plot distance in the x-axis, and in the y-axis, we are going to plot the receive power. So the variation of the receive power with distance, we are going to do for the frequency 2.4 gigahertz. Okay. The second plot is variation of the path loss with distance, and we are going to do this for 2.4 gigahertz. So these two are different ways of simulating the program in Python, and we are going to get two plots of this. Now, based on this two plots, you're going to actually use, so I'm just going to show, suppose we have this here, simple plot like this. You'll have D here, and suppose you have the receive power here. So how is it going to reflect here? So receive power is actually decreasing exponentially as you increase the distance. So this would somewhat look like the curve that you're going to get by simulating this parameters here. So from this, what can you conclude? You can conclude that as the distance is increasing between the transmitter and the receiver, the receive power is reducing. By what factor? Receive power is inversely proportional to the square of the distance between the transmitter and receiver. So square means even a minor change in the distance will cause a severe impact on the receive power. Similarly, path loss, you will have the path loss in two factors here, in y-axis path loss and distance in the x-axis. You'll find that path loss is minimum when the distance is 0, and path loss increases as you go on increasing the distance. So this is a reverse curve for path loss here. So if you see, receive power is exponentially decreasing, path loss is exponentially increasing, but at the end it would saturate to some value. So from here, what you can conclude, that as distance is increasing, path loss is also increasing. So this is how we are going to evaluate the performance of the of a wireless communication channel, how it is impacting the transmitted signal when it is propagating through this channel, and this factors of how the antenna gain, how the frequency, how the distance between the two antennas or the transmitter and the receiver are going to impact on the received signal power. So basically, this is what we are going to do in your lab session. That is for this assignment here. I'll share the lab assignment for you so that you can go through it. But this is the main factor for this. We are going to use the steps, like step 1, step 2, step 3, like this. You'll do the calculation. And for this Python code, you can use any medium that you're using. You can use your Google Colab. You can use any other medium, but you have to simulate this in Python, define the parameters, define the formula, and plot the variation in graph, and then you generate a conclusion, or you put one remark how the variation is affecting, what are the factors that are affecting the different parameters and how they are getting affected, just one conclusion from that. So this is our objective from this lab session, understanding how different parameters are affecting the receive power, I mean the signal received at the receiver end, how the power is varying with respect to the distance and how it would vary with respect to frequency of the transmitted signal. So when lambda is varying, what will happen? When the distance d is varying, what will happen? If I change the transmitted power, what will happen? If I change the transmitted antenna gain, what will happen?